Okay. So first, let's know that luminescence dating was first developed to date ceramics and heated objects. It became an important method in archaeology because it can date different minerals from materials like quartz and feldspars. And it can date beyond the C14 age range, which is 50,000 years ago. It can be dated also for materials that exist in sites like the deserts or other sites that lack for organic preservations. This method has been illustrated in this diagram, which can show different environments where luminescence dating can be applied, including, for example, quaternary glaciation, dune buildings, fluvial activities, and Lewis records, in addition to the archaeological sites. Here I shall introduce the basics of OSL dating with case studies of its applications. First, to understand the main principle of the OSL dating. Luminescence dating is based on storing energy in some minerals like quartz and feldspars by receiving radiation from the surrounding environment. After a long time of exposing to radiation, the mineral capacity to store energy reaches its saturation level, such as in this line. But when the mineral is exposed to heat or light, this energy is completely reset back to zero. This resetting energy is a target event that we usually try to date, because after that, the mineral again starts receiving radiations from the surrounding environment and start to rebuild this energy back. So when we do the sampling, we actually do date this target event, the last heating or the last exposing to light. We do that in the lab after extracting the quartz and feldspars from the material, like say pottery shards or depositions, sedimental depositions. The extracted minerals are then when shine up or let light source on it, allowing the luminescence signal to be released again from the mineral. We do detection for this luminescence signal, and by knowing the amount of the energy stored in these grains and knowing the amount of the radiation in the past, especially the rate of irradiation in the past, we can calculate the age. And this is what is known as the OSL dating. The physics of this phenomena, the luminescence signal, is usually understood in the basis of the energy band model. Minerals like quartz and feldspars contain lattice charge defects formed during crystallization or subsequent exposure to ionizing radiation. These charge defects are potential sites for electron storage with variety of trap depths energies. The interaction of radiation with an crystal provides the electrons energy that pushes them up to the conduction band. When they reach the conduction band, they diffuse rapidly into the band or the gap energy. In the gap energy, we have the defects of this crystal, which is known as luminescence traps or electron traps, like T1 and T2 in this case. The deeper the trap is below the conduction band, the more stable and the longer it can hold the electron for a longer time or during the lifetime. This habit, or the electron stays in these traps until a source of light or heat stimulates this electron, allowing it to diffuse or to be detrapped from these centers. When it detraps, it loses part of its energy, which comes out as a light called luminescence. And this is the principle of luminescence, is how to detrap these electrons stored in these traps. And where is that drop? Is it in the deep traps below the conduction band, which is like more stable during the geological lifespan, or it is in the top of the traps, which is less stable, in most cases like the feldspars. And that's what it came to the other part of this principle, is which mineral we'd use for dating using the luminescence dating, quartz or feldspars. In general, both minerals are used for luminescence dating. However, selecting the mineral is usually depends on the abundance of this mineral in the sample itself. They also depends on the luminescence characteristics for potassium, feldspars, or quartz. For example, the quartz luminescence signal breaches rapidly in sunlight compared to the feldspars, and the signal is more stable over geological time period. However, some quartz grains could have no sensitivity for OSL signals, and some grains could emit no signals at all, while feldspars, for example, is brighter in its signal, but during the geological time period, it fades and it could lose some of its electrons trapped in the luminescence centers. How we use the luminescence signal to calculate the age? This is carried out by using the age equation, which is known as the dose divided by the dose rate. These two parameters are very important to specify in the laboratory. First, I will speak how we calculate the dose. The dose is the amount of radiation dose absorbed by the sample throughout its time span that is responsible for creating the natural luminescence signal. It is termed in literature as DE, or equivalent dose, and use the unit of gray. Determining the equivalent dose is usually based in comparison of the natural luminescence signal already stored in the sample, emitted from the sample in the first stimulation we do in the lab, and comparing it with other luminescence signals that we can regenerate in the sample by subsequent irradiation we do in the laboratory. Therefore, there's two different approaches that is followed in the laboratory to define the equivalent dose. The first method is known as the additive dose, and the other method is known as the regeneration dose. The regeneration dose usually is applied for the same aliquot or for the same grains. We use either quartz or feldspars grains. We illuminate it using blue LED for quartz or infra LED for feldspars, allowing the natural luminescence to be stimulated and released, and detect this energy using the photon detector. And here is the energy, the luminescence intensity of the natural signal from the sample. Later, we irradiate the sample, the same sample again, using a beta source, and repeat the measurement for the same sample. And this time we use the signal, with the signal, and we call it the regenerated luminescence signal. This process is done several times or in several cycles. To now calculate the equivalent dose, we plot what is known as luminescence response to dose curve. This curve is actually plotting the intensity of the luminescence signal against its given dose that regenerated this luminescence signal. Like in this case, we have the 3 regenerated dose, so 3 signals intensities plotted against them. The equivalent dose is then calculated by interpolating the intensity of this signal with the curve and identify the equivalent dose. However, it has been observed that luminescence sensitivity of the grains changes from measurement to measurement during the regeneration of the signal in the laboratory, showing sometimes inaccurate interpolation. The inaccurate interpolation or the sensitivity change also happens because of the preheat step that we use during the measurement. And the preheat before stimulation is usually done to get rid of the unstable traps that could affect the real equivalent dose. Therefore, to overcome this problem, a new measurement approach has been introduced by Mori and Wintel in 2000. It's called the single aliquot regenerative dose, or SAR protocol. In this procedure, we use the luminescence response to affix this dose. That means incorporating another irradiation dose, but this time is fixed, is not over or added dose. And we use the correction of the luminescence signal, the natural or the regeneration dose, to this dose. And here we, as you see in this plot, we have a three regeneration dose. With each regeneration dose, we were putting the ETIS dose and take the ratio between the signal emitted from the regeneration dose to the test dose. The equivalent dose is then interpolated by the curve, also by correcting to the test dose, and we have the equivalent dose calculated in this interpolation. This method has become the routine method for the measurements of equivalent doses in quartz. It has been widely applied for both heated quartz and not heated quartz, and been shown to give a very accurate and consistent independent age control. In feldspars, and as we mentioned between the mineral selection, in feldspars, there is a chance of existing non-stable traps or luminescent traps. Therefore, this technique has been updated for feldspars by introducing two kinds of stimulation and two different temperatures. It's called the IR signal at elevated temperature. That means stimulation first, the luminescence, natural or regenerated luminescence, at low temperatures around 50 centigrade, and this is called the IR50. And then illumination using higher temperature like 290, and this is called the IR 290. Given then the test dose, which is fixed in all cycles, and repeating the stimulations at the two different temperatures. This allows, the method is allowing for us to empty the signals from the unstable traps before measuring the signal from the more stable traps without any contribution of those unstable ones. This method has been now routinely used for feldspars dating. Some people use 290, some 180. There is methods of correcting these temperatures and method of testing these temperatures, which is best for the samples we are using. The apparatus that we use for OSL measurements, which is known as the OSL reader, composed of three main components: the beta source, which is used to irradiate the samples to create the luminescence signal in the lab; the photon detector, which can detect the photons or lights released from the sample and convert them into digital connected to the computer; and the LED lights. As we mentioned before, we use a blue LED if we are dealing with a quartz sample, and we use infrared LED if we are dealing with feldspars. Samples are when used or loaded to the reader using aliquot holder. Usually we use a small size of stainless steel discs, about 1 centimeter in diameter, and grains hold in this disc, usually grains up to 100 grain. More advanced readers use the procedure what is called single grain measurements, where the discs loaded to the reader have 100 holes. Each hole can have 1 grain of quartz or feldspars. The second term of the age equation, which is the dose rate. The dose rate is the rate of storing energy since the last resetting of this luminescent signal. It originates from exposing mineral to ionizing radiation, such as alpha, beta, and gamma. It donated or used in the literature as DR, and the unit of measurement is gray per kilo year. The source of ionizing radiations are natural radioactivity and cosmic rays. Usually the contribution from the cosmic rays are very small in the fraction. Energy is absorbed as alpha and beta particles and gamma rays emitted during the decay of natural occurring radionuclides. As you can see that radiations has different penetrations in the matter. So direct estimating of the dose rate is a complex process. Therefore, dose rate estimates is based on the infinite matrix concept. In the infinite matrix concept, all of the specific energy emitted in the medium is also absorbed by the same medium, provided that the medium has a homogeneous structure with 1 meter at least of dimension. The rate of energy emission in an infinite matrix is also calculated from the concentrations of the relevant radionuclides concentrations in the sample. And we usually measure 3 radionuclides: deuterium 232, uranium 238, and potassium 40. The water content in the sediment also affects the dose rate, because water can absorb the energy emitted from the radionuclides. Therefore, it reduces the effective dose rate into the sample. The radionuclides concentrations can be measured using different counting and spectrometry systems in the labs, such as gamma scintillators, beta and alpha counters, ICP-MS, neutron activation analysis. And then concentrations are converted later into the unit of gray per kiloyear. Before we finish the age equation, we have to say that the age equation is based on 2 basic assumptions. Those assumptions are that the luminescence signal has been fully reset or bleached to 0 by light or by heat before burial or during its burial time. But this could be always true if we are dealing with heated materials up to 500 centigrade. That is true for ceramics, for pottery, but for stones or heated stones, sometimes the heating did not reach the whole bulk of the stones, so we don't have a fully resetting for the stones. For also resetting by light, this could be true if the grains has been deposited by wind blown or by, for example, a water wash. But sometimes it's not fully reset in these 2 processes, and then the date is actually overestimating the real date that we target. The second assumptions that hold it true or should hold it true for the age equation is that dose rate has been constant through time. To check for the reliability of the OSL dating, by study made by Mori and Ole 2002, they made a comparison between OSL ages for quartz from different environments, Aeolian, freshwater, marine, or glacial, for about 53 samples. The line crossing these samples, the comparison between OSL ages and independent age control, estimated in kiloyear, the line is 1-to-1 line. As you can see, there is a great agreement between the OSL ages and the independent age control, except for a few samples that they are above the line. This actually the samples showing that here they had not in or incomplete bleaching of the OSL signals, and that's why they are overestimating their real ages. How do we collect the samples for the OSL dating? OSL samples are light sensitive. Therefore, collecting the samples are meant to conceal them from light until they are processed in the lab under reduced light. The most common procedure used for sediment layers is to collect the sediments into opaque tubes, such in these cases, which are hammered into the section. It's important to specify always the target layer that we want to collect the OSL sample for. For example, avoid the layers that show evidence of disturbance or evidence of post-depositional mixing, processes like, for example, bioturbation, soil formation, desiccation, cracks, that can mix between the grains from different layers, and then you have mix of sedimentary profiles and OSL ages. Sometimes hammering the tubes into the section is not always effective, or they are not possible. So you have to adapt a method that can help you to collect your samples. For example, here they are doing a vertical coring in the surface of the area targeted. Here I'm using hammering the tubes, but because archaeological layers in the Iron Age are very thin layers, so the diameter of the tube I used was barely 1.5 centimeters. In this part, they are collecting it as a block because the sediment layers is very intact, and also hammering the tube will be difficult. In the final one, we could not hammer a tube because it is about rich with rubbles and pebbles, so tubes will not be easy to penetrate into the section. So we had to collect the sample under cover and using only the red light under this cover. You can repeat the process at night if that helps. Always record the information on the latitude, longitude, or the elevation of the site and the burial depth of the sample, because these 4 parameters affect the calculation of the cosmic ray contribution to the dose rate. Photographs and the profile sketches should always be included during our study because it helps us to illustrate the stratigraphic relationship between the samples. In the lab, samples preparation process is aiming to extract feldspars and the quartz grains for the OSL measurement. This diagram is from Mori et al. At 2021, illustrating how the process of the sample in the lab is made. First of all, we take, if we are using the tubes, we take the inner part of the tube. We are expecting that the entity of the tube has been exposed to light during the sampling process. So we avoid them and you use only the inner part. The end part only used for the radiant light concentrations measurement. First, we do the sieving. The sieving, or the difference of using grain size, it is important for the measurements, and it's important also for calculating the dose rate, because the dose rate absorbed from the radiant light concentrations is also affected by the size of the grain. Usually, scientists use with the different grain size, but the most preferred one is using the one between 180 to 250 micrometer. Below 63 micrometer are avoided because this is rich with the clay and they don't have enough of a quartz or feldspars. The second step after sieving is cleaning the material from calcites and from organic materials. This is done by washing the sample with SCL. 30 minutes usually is enough, but you can repeat the process until you see the until you see the evaporation and the reaction with the calcites is resist and stopped. Cleaning from the organics is using hydrogen peroxide. It could also be for 1 hour, but if you feel that your sample is rich with organic, you can repeat the process. It could take several days if they are very rich with organics. The second step is either separation, feldspars from a quartz, or if we are only want to use the quartz, then we go directly to cleaning the sample with 40% of HF. The 40% of HF can directly remove any kind of feldspars in the sample. But if we wish to use also feldspars for measurements, we do the separation of the two minerals using the density differences between the two minerals. And that's called the heavy liquid separation. The heavy liquid separation is using a liquid of density 2.58 gram per centimeters cube that allows for feldspars to float in top because they are lighter, and for quartz to be in the bottom because they are heavier. After we separate the two minerals, feldspars now is ready after washing to be used, but the quartz have to be cleaned up again with 40% of HF. Extra step of washing with the diluted HCl is also applied. And now the two minerals are ready to be used for the measurements. Now I will talk about the 3 case studies for the OSL measurements. The first case study is for Lake Algae and the geological perspective changes in the evolution of Petra region in Jordan. Petra, which is located in south of Jordan, has been known for its engraved facades in the sandstone. But actually the region has been in different shape or environment 60,000 years ago. In this study, we used the OSL and other analytical investigation to identify the remains of Bellew Lake in the area surrounding the archaeological part of Petra. If maybe this image is not clear very well, but this is like this is an aerial photo where it shows the Petra, the current Petra or the modern Petra, archaeological sites like al-Bayara, Sayhoun, and Ras Ftahi in the south. And as you can see, it is completely a dry area. But when archaeological studies and archaeological surveys has showed that human settlements goes back to the late Paleolithic period and through the end of Neolithic periods, were concentrated in the high areas of the Petra region, in the mountains or in the highest elevation of this basin or this region. The beginning of habitation in the core of Petra, which is now has started at the Nabatean time, which is about 300 BCE. These evolving settlements from the highest elevation down to the core of this region has to do with the changing climate and topographic conditions in the past. So we use the OSL to understand this geological history of the region of Petra, which included, at the end of our conclusions, the presence of an ancient lake, which we named it Lake Algae. Lake Algae, as you can see, during the Paleolithic age, has a wide and open area. It started from Wadi Namila in the north and Ras Ftahi in the south, and they have a drainage and leakage in the south. The lake has shrunk by time, and this is a simulation for this lake during the Paleolithic and early Holocene age. We collected the OSL samples from deposits from different elevations and from depositional sections around the basin and at different near different archaeological sites. Based on the overall OSL results, the edges of the thick uniform layers were found to be consistent with the rapid depositions of the sediment. This is presumably caused by hydrological changes and tectonic events which cause the change in the drainage of the lake body, making the area open for a human habitation to take place. And so if we want to go step by the timeline of the Lake Algae, it will be as follows. During the Pleistocene, at least 65,000 years ago, the Lake Algae was an open wide lake which extends from the north at Wadi Namila down to the south at the Ras Ftahi, which about 50 kilometers, and the shorelines was about 1,060 meters above the sea level. This high level has dropped to 960 meters toward the end of the Pleistocene and before the Natufian period as a result of tectonic movement along the fault of the Dead Sea Rift, allowing the drainage to be in the south at Ras Ftahi and Wadi Ghurab. This Natufian settlement have been restricted to the margins of the basin. They still did not go down of the 90-60 meters above the sea level habitations, places. As the climate dried toward the beginning of the Holocene, the lake bottom became wetland in this area and hosting reed communities, shrublands, which was still not suitable for habitation. The situation attracted Neolithic farmers to settle in the area, but they still was using the mountain tops and not deep down in the basin. This continued under the Chalcolithic and Iron Age settlements, only using the high tops of mountains for settlement. But accelerating of the uncovering of the sediments and more drying times and the changes in the environment, the lake area become more clear and more suitable for habitation, and also exposing the Paleozoic bedrock of the site, allowing for the carving of Petra facades to be around 2,000 years ago. In the second case study, which is applied to rock art and vast environment using mud wasp nest in northern Australia. In the Kimberley site in northwest Australia, there's a lot of rock art that's engraved by the ancestors of the Australian Aborigines. The site is characterized by an extraordinary rich records of these rock arts that has not been able to be dated because of the lack of the organic matters that can be used for the C14 dating method. However, these rock arts are covered with mud wasp. The mud wasp are special nests or houses that are built by special wasp that collect they gather the mud from surface sediments from the margins of streams and pools, which means that they were exposed to a quartz to sunlight during collecting. And it transport this mud into the surface or the ceiling of these rock arts to build their nests. The final exposure happens when these wasps build their nets on the rock art and construct the net over the old layers of older nests. In this study, authors collected 7 nests at night using red light. The thickness of the nest ranged from a few millimeters to several centimeters. Knowing that the wasps prefer to build nests or build their houses in a previous and older abandoned nests, they used each nest as several samples. So they kind of divided each nest in several portions, and they measured each portion and related it to the depth of this nest. The thickest of this nest that they measured was about a few centimeters, they divided it into 7 portions. The top surface of this nest was about 110 years. In the middle of this nest was about 600 years, 270 years, and the deepest of this nest was about 600 years. That means that the house of this mud wasp was built in a time span from 100 to 600 years. And that was the youngest nest they found. In another measurements for another 2 nests, they found the ages deep into 70,000 years ago. And that could be the minimum age of these rock arts, because that means after the rock art was there, it's very likely that the building of these nests happened directly, and that's the minimum age, or happened later, but about 70,000 years before now. In the last case study, it is about Kolban Bani Murra in Jordan. In this study, it's an example of dating sediments that has not deposited by natural activities, rather by human activities. Hulban Bani Murrah is a site which is located in the southern part of Jordan, in the desert area, very remote area, about 30 kilometers north of the Saudi Arabia. The site is assumed to belong to the Chalcolithic culture about 5,000 years before BCE. It includes party of megalithic burials field connected to a water management system. The remains of 9 wells and watering system existed in the Wadi floor, and the well complex from which the samples were taken is formed by a mixture of reddish silty sediments of unknown origin. But it is assumed that this reddish sediment is actually the same components when they dug the well. They dug the well, they took off the sediment, they put it aside, exposing it to light, and then using the same sediment to lining up the walls of the well that they dug. So the samples were taken from this wall lining sediments. 2 OS tubes were hammered into these sediments, and we could extract both quartz and feldspars for OSL dating. It was to notice that only 1 C14 could be extracted from this layer of sediments, and the age was 4,500 BCE, around that time, Chalcolithic times. When we dated the quartz and feldspars for the 2 samples, first of all, we noticed that both quartz and feldspars were in good agreement with each other. And both samples were in good agreement with the only radiocarbon sample that exists in the site. This supports the potential of using luminescence dating for not only geoarchaeological landscape, but also for samples that has been deposited by human activities. And that is shown by the good agreement between both quartz and feldspars, which means we have a good bleaching and resetting of the signal when a human was using this sediment, and a good agreement between radiocarbon ages, which means that we are dating the target time of the target activity. As a conclusion, I can say that OSL dating has a very wide dynamic range. It could date from 1 year up to 200,000 years. The SAR protocol for quartz is very precise and accurate, and it is now considered as a conventional practice for dating material. Applications cover many Earth surface environment. It could date heated materials, ceramics, bricks, slags, or heated rocks. It could date sediments by natural depositions or human activities. And as I will present in the next class, it could date also rock surfaces, also from human activities or natural setting. And thank you for listening. I'll stop recording now.